This is a velocity time graph of a moving body. What does this graph tell us? Here, this is the initial velocity of the body, which we'll call as u. Initial velocity. And in this case, we see it is 3 meters per second. The velocity of the body then slowly increases till the body then reaches this point here, and the velocity here we see is 7, which is a final velocity. So the final velocity is 7 meters per second. That is an acceleration A. The velocity of the body keeps increasing, and that acceleration is called A. The acceleration in this case is constant because we see that the line is a straight line. The increase is a straight line. Another thing we need to know, here O is origin. We call this point as A, which is the initial velocity. We call this point B, which is a final velocity. Now this is OA. Here this is OA. And we know that OA is equal to u, which is 3 meters per second. And on the other side, we have here this segment. We'll call this segment as BC. And we see BC is equal to 7, which is the final velocity. This is 7. Or we can say which is V, and which is 7 meters per second. If I draw a line, straight line here, I will get this point as D. And how much will CD be? This is CD, and CD will definitely be equal to OA. So we know CD is equal to OA, which is also equal to U. So this is here now U. We need this information for the derivation of the first equation of motion. So here again is a velocity time graph of a moving object. It has an initial velocity, say U, and then the velocity then increases to a point V. So here we have u is the initial velocity, and v is the final velocity. So this is the initial and final velocity. Let's mark the points. We need this point, which we call as O, origin. Then we have here this point, we will call it as A. And then we have again here this point, we'll call this as B. We join this line straight down here. We call this point here as C. We'll also join this horizontally, and we call this point here as D. From the definition of acceleration, we know acceleration is change in velocity over time. So acceleration will be change in velocity is final velocity minus initial velocity over time. So acceleration will equal to, now what does V represent? Look up at V. This is our V here, which is BC. So for V, we will put BC minus, now what is our U? Here is our U, OA is our U. So for this, we put minus OA. And what is the time taken for this change to take place? That is OC. OC is the time taken, and that we write T, which is T, so OC. So we know our U here is OA, our V is OC, and the time taken for this T is denoted as OC. There's another point we need to note is OA is equal to CD. So we have OA. So now for acceleration, we do BC minus, for OA I'm putting CD over OT, which is times CT. Well, look up in the figure and let's see what is BC minus CD. So here is BC and minus CD, and this is CD. So BC minus CD is this. Here, this one is BC minus CD, which we know is BD. So we write that now. So we go again, we calculated A equal to BC minus CD over T. So A equal to, and we have seen BC minus CD is nothing but BD. So write that. So we have BC minus CD equal to BD over T. So we have BD equal to AT. And this is very important because we are going to use this many a times while deriving the equation. Let me put it in the figure. We have BD, and this BD is always equal to AT. We also have seen earlier that CD is nothing but U. And this entire BC here is V, equal to V. It's the same figure now. If you look up in the figure, what is your BC equal to? This entire BC, this full BC is equal to DC plus BD. Let me show it up in the figure. So it is equal to this CD plus BD, right? And that's exactly what I have written. So we have now BC, and we know our DC is U, and our BD we have found is AT, and BC we know is V. So V equal to U plus AT. That is our first equation. V equal to U plus AT. I'll just go over it again. So we had BC equal to DC plus BD. That is very simple. It can be seen in the equation. For BC, I'll rub BC. I know BC is equal to V. Now look up and see what is DC. DC is out here. This is DC, and that is, we see, is U. And what is our BD? BD is here. This is BD, and we have calculated BD and see that it is AT. So we have an equation V equal to U plus AT. This is our first equation of motion. Now we go in for the second equation of motion. Again, here we have the velocity time graph of a body moving, having an initial velocity, say U, and a final velocity V, and the change in velocity takes, say, time T, just like the Earth. Now to find the distance traveled by this body in time T, the distance travel, and we put the distance as S, will be the area enclosed by the velocity time graph. Now let's see which is the area enclosed by the velocity time graph. So here is a velocity time graph. This entire is the area enclosed by the velocity time graph. So here I have shaded the area. Now this area is equal to the distance S. So if I can calculate this area, that's the area of OA B and C. That would give me my distance traveled by this body in time t. So I'll write distance S equal to area of OABC. Now this area I can divide in two parts. If you notice, I can draw a straight line here. I will get this area. I'll mark this point as D. So this is an area and it is a rectangle. And the other area would be this triangle. We'll add up both these areas, will give us the total area. So these two areas I need to find, and this is the area of the triangle. So the area of this entire will be area of, it's in green, this area plus this area will be the area of OABC, that is area of a rectangle plus area of triangle. Now area of rectangle is always length into breadth, and of course the triangle we know area is half base into height. Now let's see what's the length and breadth of this triangle. Here is the length of the triangle, which we know is T, and here is the breadth of the triangle, which we know is U, that is equal to OA. OA is U. So for this triangle I have UT, length into breadth, plus, now we have to go to the triangle is half base into height. Now for this triangle we see that this is the base. Let's mark the base. This is the base, which is again T, and the height of this triangle is here, BD. And if you remember earlier, we have found this as AT. In the earlier one, we proved that BT equal to AT. So here we have half base into height, that is half. This is the base, which is T, and the height is AT. So now the area, the total area S equal to UT plus half A. T and T would give me T square. So this is my next equation. The area equal to, or distance travel, is SUT plus half AT square. To go over it again, in this sum we have to calculate this entire area. And this entire area is made up of two parts. One is this green rectangle, and the area of the green rectangle is length into breadth. This is the length and this was the breadth. So this area equal to length into breadth, UT. And then we have the area of this triangle. Now the area of the triangle is half base into height. So this area is half, and the base here, this is the base, and here is the height. So the base we know is U, and is T, not U, it is T, and the height is 80. This is the height 80. So this is half AT square. Then we add up UT plus half AT square. Now for the third equation, here again we have same initial velocity is U, final velocity is V, here U, final velocity V, and the time taken for this change is T. Now for the third equation, again we find the distance. So the distance below the velocity time graph will give us, the area below the velocity time graph will give us distance. So this is the entire area. This entire area will give us distance. And this is what we are going to calculate. To find the distance, we have to find the area. So for the third equation, we will consider this area that we need as a trapezium. If you notice, this is a trapezium. Here is one parallel side, this is the other parallel side, these are the parallel side, and this is the distance between the parallel side. So we will now calculate this area as a trapezium. So here we say distance, which is given as S, is in this case now area of trapezium. And the name of this trapezium, of course, we know is OABCT, this trapezium. So trapezium area OABC, this trapezium. And when it comes area of trapezium, the formula is half the height of the trapezium and the sum of the parallel sides. This is formula of trapezium. So for this it will be half. Now who is the height of this trapezium? We see here OC is the height of the trapezium. So we will put OC. Here OC is the height. And the parallel sides. Which are the parallel sides? One is OA and other one is BC. So let's put the parallel sides here, and that is OA plus BC. So the distance S that we are calculating is half. Now we know this OC, this OC is nothing but T. So let's put that up. So for OC I'll put T. For OA here, this is OA, and you know OA is U. And BC till here we know is V. So let's write that out too. So you have U plus V. So S equal to half T U plus V. Now earlier we have learned that A equal to V minus U over T, which means T equal to, I take this A on the other side, so I'll get V minus U over A. So this is exactly what I'm going to substitute here. So S equal to half. For this T, I'm going to substitute this value. So here for the T, I'm going to put V minus U over A. And this I'll just rearrange. This I'll do V plus U. Now, if you recollect the formula of A minus B, A plus B is A square minus B square. And that's exactly what we're going to use here. So for here, V minus U and V plus U, I'm going to put V square minus U square over A. So let's go back again. So S we had half T V plus U. So S T half. For the T, I put V minus U over A. And this was V plus U. So S equal to half. Here A minus B, A plus B, and A minus B, A plus B we know is A square minus B square. So this would be now V square minus U square over A. So S equal to V square minus U square over 2A. I take the 2A on the other side. So 2AS equal to V square minus U square. I take the U square on the other side. So 2AS plus U square equal to V square. So I have now V square equal to U square plus 2AS. And this is my third equation.